In the 1960s, NASA built one of the most advanced spy cameras ever imagined, so massive and powerful it could see details from orbit that no other satellite could. But despite all this ambition, the camera never flew. Why? Because it was too powerful, too complex, and too risky. This was the Manned Orbiting Laboratory, or MOL, a secret program designed to put astronauts in orbit operating this enormous mechanical eye. It was meant to be the pinnacle of reconnaissance technology, a camera that could reveal secrets from space. Engineers poured years into lenses larger than a person, film storage so vast it could hold thousands of images, and mechanical systems so precise that even a small misalignment could ruin months of work. Astronauts trained for months to operate it in zero gravity, orbiting Earth at 17,500 miles per hour, while the machine's components had to withstand radiation, extreme temperatures, and the violent forces of launch. And yet, despite all this preparation, the project never left the ground. Why did such a powerful machine never see orbit? Because the world around it, budgets, politics, and technology, could not support it. Even as MOL pushed the limits of human ambition and mechanical engineering, unmanned satellites were improving, capable of taking high-resolution photos without risking humans or huge spacecraft. The question remained, if humans could do it, and machines could do it, what was the point of this enormous, expensive, and dangerous project? It was canceled before a single photograph could be taken from orbit, leaving behind a legacy of ambition, caution, and wonder. What was the MOL spy camera? It was a gigantic reconnaissance camera meant to be operated by astronauts in space, capable of unprecedented resolution. Why was it built? The United States wanted better eyes in orbit during the Cold War, technology far beyond anything before. Why didn't it fly? The camera and spacecraft were too big, too complex, too expensive, and too risky for the program to continue. Could machines have done the same job? Yes, unmanned satellites were rapidly improving and could accomplish the same missions safely and cheaply. Why does this matter today? MOL's designs influence future spy satellites and remain a symbol of human ambition, pushing the boundaries of possibility. Stage 1. The birth of a giant. The story begins with the Cold War in full swing. The United States wanted eyes in space that could surpass anything the Soviet Union had. The MOL program was conceived to put astronauts in orbit, operating a giant spy camera that could photograph Earth in unprecedented detail. Engineers built enormous mock-ups, tested components in vacuum chambers, and simulated operations for astronauts on the ground. Every bolt, gear, and lens had to be perfect. Astronauts trained relentlessly in simulators, learning how to operate the massive camera while floating in microgravity. The scale was overwhelming. A single camera weighed thousands of pounds. The lens system rivaled the size of a small car, and the film reels had to store thousands of images. Questions constantly arose. Could humans really operate such a complex system in space? Could it survive launch and orbit? Could the benefits outweigh the immense risks? Every answer leaned toward yes, but the risks and costs were still climbing, threatening to bury the project before it began. Engineers often worked late into the night, testing every component repeatedly to prevent a single catastrophic failure. Astronauts ran through mock missions hundreds of times, learning to operate the massive camera in zero gravity. Every new simulation revealed how fragile the system could be if not handled perfectly. The pressure was enormous. One mistake could destroy months of work and millions of dollars of equipment. Despite the challenges, the team pushed forward, driven by the vision of having the most powerful eyes in space. Each lens, bolt, and reel of film was meticulously calibrated, a testament to human ingenuity and precision. The MOL spy camera was not just a machine, it was a symbol of ambition, daring, and the limits of what humans could control in orbit. Stage 2. Designing the impossible. Designing the MOL camera was a feat of engineering unlike anything before. It had to capture Earth in astonishing detail while being manually operated by astronauts. Lenses had to focus perfectly, shutters had to move precisely, and film had to survive cosmic radiation. Engineers spent years perfecting the system, creating machines that could survive violent launches and extreme conditions in orbit. Astronauts trained with mock-ups, practicing delicate maneuvers in zero gravity, knowing that one mistake could destroy months of work. Imagine operating a camera the size of a small car while orbiting Earth at 17,500 miles per hour, keeping it stable and focused on moving targets below. The machine demanded skill, precision, and courage. Every day brought new challenges, testing massive lenses, stabilizing heavy mechanisms, and balancing power with weight. This camera became almost alive in its presence, a symbol of human ambition and technological risk. The camera's components were so complex that even small misalignments could ruin an entire mission. Astronauts trained tirelessly with full-scale mock-ups, learning to operate the delicate machinery under simulated orbital conditions. Every gear, every shutter, every lens had to perform flawlessly despite the forces of microgravity. Engineers created redundant systems to ensure nothing would fail, yet the sheer size and complexity still posed enormous risks. The project became a race against both physics and time, with deadlines looming and pressure mounting. Each successful test increased confidence, but also reminded everyone how fragile the system truly was. Stage 3, the problems mount. By the late 1960s, the challenges of MOL became clear. Costs skyrocketed far beyond initial estimates, technical problems persisted, and political pressure grew. Unmanned satellites were improving, able to accomplish reconnaissance without risking astronauts or spending billions. Military planners questioned the need for humans in orbit when automated satellites could do the job more safely. The camera's sheer size and complexity became a liability. Every component was scrutinized, delays mounted, and the program teetered on the edge of cancellation. This enormous advanced technology, which could have given the U.S. unprecedented eyes in space, suddenly faced the reality that it might never fly. The camera was too powerful for the time, and the world around it could not handle it. As costs soared, political pressure mounted to justify every dollar spent. The military began questioning whether human-tended cameras were truly necessary. Unmanned satellites were becoming faster, cheaper, and more reliable, making the MOL program seem almost obsolete. Delays piled up as engineers struggled to perfect the system while staying within budget. Every technical challenge became a question of practicality. Could it really fly safely? The team's hard work was overshadowed by a growing sense of doubt from those in power. Stage 4, too powerful to fly. In 1969, the MOL program was canceled. The camera, despite years of development, testing, and astronaut training, never left the ground. It was too advanced, too large, and too expensive for human spaceflight. The political climate, budget constraints, and emerging satellite technology made the project impossible to continue. The camera's design, however, was not wasted. Lessons learned helped improve future unmanned reconnaissance satellites, optical systems, and orbital cameras. The astronauts, engineers, and planners moved on with knowledge that would inform space projects for decades. But the MOL camera itself remains a monument to ambition halted, a machine that could see more than anyone expected. Stopped by limits beyond its control, the camera's sheer size made the spacecraft almost impossible to launch. Engineers debated every design choice, weighing performance against the risk of failure. Astronauts continued training, knowing that the slightest mistake could be catastrophic. Meanwhile, unmanned satellites were proving they could do the same job more safely and efficiently. The cost of keeping the program alive grew higher by the month. Eventually, political and financial realities forced the Air Force to make a decision. The camera, despite its brilliance and ambition, was grounded forever. Stage 5, Legacy and Lessons. Though it never flew, the MOL spy camera left a lasting legacy. Its design influenced the next generation of reconnaissance satellites, and its ambition demonstrated how far human engineering could go. It was a reminder that technology sometimes moves faster than the world can handle, and that even the most advanced machines can be grounded by politics, cost, and caution. The MOL spy camera remains one of NASA's most mysterious and fascinating abandoned projects, a symbol of what could have been, and a lesson in human ambition, risk, and innovation. Its story continues to inspire engineers and space historians, revealing the delicate balance between imagination, capability, and practicality in the pursuit of space exploration. Even on the ground, the MOL spy camera influenced the future of space reconnaissance. Engineers studied its design for years, adapting lessons to smaller, automated satellites. Astronauts carried their training experience into other missions, refining human interaction with complex orbital machinery. The ambition of MOL pushed technology forward in ways that were impossible at the time. Historians now look back and marvel at what could have been. The project serves as a reminder that human ingenuity often reaches beyond what reality can support. Its legacy is a story of ambition, caution, and the limits of power.